Okay, so in the last few classes we discussed about DH parameters, and then so how do we actually assign coordinate frames, and then using coordinate frames how do you find out the DH parameters? Basically the four parameters, the theta, A, D and alpha. So today we will see how do we actually use this one for developing the forward kinematics relationship for an industrial manipulator. So the purpose of forward kinematics is basically to map the coordinate frame at the tooltip to the base frame here. So if any point represented with respect to the tool frame, you should be able to represent that with respect to a base frame. And there will be many joints in between the manipulator tooltip and the base frame. So how do we use the DH parameters, and then using the DH parameters, how do we develop a matrix called ARM matrix to map the coordinate frames, and then use these coordinate frames to get the forward relationship is the question that we are trying to address. So the ARM matrix is defined as a homogeneous matrix that maps frame K to K minus 1 coordinates. So you have a kth frame, and a K minus 1 frame. How do we actually map these two frames using a matrix and that matrix is known as the ARM matrix. So we use a homogeneous transformation matrix, which is a 4x4 matrix, which includes the all the joint parameters and the link parameters, as well as the DH parameters what we will be using for getting the transformation. And we saw that we can use the four parameters, that is D, theta, D, A and alpha. So these are the four parameters that we are that's of interest between two coordinate frames. We will see how can we actually develop this ARM matrix using these four parameters. So assume that this is the base coordinate frame, and then you have another coordinate frame at this point given by XYZ coordinate here. So now here you can see this is the Z axis, this is the X axis, and this is the Y axis. So this coordinate frame, base coordinate frame, and these two coordinate frames we want to map, or we have to find the transformation how this coordinate frame is transformed to this coordinate frame using this parameter. So how do we actually represent this? So what we can do is we can first look at, assume that these two coordinate frames are initially aligned together, that is this x0, y0, z0 and x, y, z are initially aligned. So initially they were actually the same x, y, z here. Now assume that this coordinate frame rotated by an angle theta. Assume that this x, y, z rotated by an angle theta with respect to the z0 axis. So if it is rotated, then you will see that this will become your x, the rotated x, and it is rotated with respect to z axis. So z remains same, and then your y will be something like this. That is the first parameter theta. You can see that the transformation of this two coordinate frame, first it is rotated with respect to z0 axis by an angle theta, and then it has translated along the z axis by a distance d. So it reaches here. So first it rotated by an angle theta. So by an angle theta it rotated x0 to x. With respect to z0 it rotated by an angle theta. And then it translated by an angle d to reach here. And then it translated again along its x-axis. So this frame I am just showing it like this because it will be along the link. So it is translated along x by an angle by a distance a, and then it rotated by an angle alpha with respect to x-axis. So it rotated by an angle alpha. So z-axis actually came here, and you got this frame here. So the four transformation takes place for this coordinate frame to reach here with this orientation. So it rotates by an angle theta with respect to z0 axis, and then translates along D axis and the Z axis by D, and again translates along X axis by by a distance A, and then rotates with respect to X by an angle alpha to get the new Z axis. So by these 4 transformations, you are actually getting these 4 transformations, individual transformation for this coordinate frame to get this coordinate frame. So the mapping between these 2 coordinate frames can be represented using these 4 transformations. So that is why we need these DH parameters to understand how this particular coordinate transformation happens from the original coordinate frame. So this is what we are trying to understand here. Okay, so we have this transformation. So it moves and then it finally reaches here. So rotate Lk minus 1 about Zk minus 1 by an angle theta, and translate along Zk minus 1 by dk, and then translate along Xk minus 1 by ak, and then Lk minus 1 about Xk minus 1 alpha k. So all with respect to its own frame. So all the transformations are with respect to its own frame, not with respect to a base frame. So all are with respect to its own frame, and therefore what we will do to get the full transformation, it's a composite transformation, right? So what we need to do a post multiplication, right? So you will be getting this k to k minus 1 transformation, that is the kth to k minus 1 transformation, how the k minus 1 and k are related, or any point in k can be related to k minus 1 by using this transformation k to k minus 1, which is R, T, T and R. So these are the 4 individual homogeneous transformation we will be using in order to get the composite transformation of the coordinate frame from k to k minus 1. So this is known as the arm matrix or the homogeneous transformation matrix from k minus 1 frame to kth frame, or the source frame to destination frame. Okay, so this is what actually the coordinate transformation matrix. So between any 2 coordinate frames of the manipulator, any 2 adjacent coordinate frames, we will be able to find a transformation matrix with these 4 parameters included. Out of these 4, only one will be a variable. So finally you will be getting a matrix with 1 variable, and that relates the coordinate frame k to k minus 1. So this is basically the arm matrix or the homogeneous transformation matrix between 2 coordinate frames of the manipulator. Okay. Alright. So how do we get this? So first you get these matrices. So you know how to get the fundamental homogeneous rotation matrix with respect to 3rd axis. Then translation matrix, again rotation matrix with respect to x axis, rotation matrix, translation with the x axis, and rotation with the x axis. So all these 4 transformation matrices, we know the fundamental rotation matrices and translation matrices. Multiply these matrices and then you get the final transformation matrix, which is this one, k to k minus transformation. So this is the final DH matrix which relates to adjacent coordinate frames with the parameters, all parameters theta, alpha, a and d. So you can see this is a function of all these parameters theta, a, alpha and d, and k to k minus 1 is obtained by this relationship. And we saw that if we have multiple coordinate frames, we will be able to get theta 1 to theta n, similarly a1 to an, etc. for any manipulator frame, and therefore we will be knowing all this information, and therefore we can actually find out t1 to 0, that is if you have a manipulator and the base frame is 0, the next joint is 1, then we can find out the transformation from the first joint to the base frame by as a t1 0, and similarly we can actually get t2 1, t3 2, etc. tn to n minus 1 we will be able to get, because we know these parameters, and therefore we will be able to get these transformations between adjacent frames. You will be able to get as a transformation matrix n to n minus 1. So the only thing what you need to remember is this matrix. If you can't remember, then you need to go to the fundamental matrices and then multiply it. Otherwise, if you can remember this, then you don't need to worry, because what we need in forward kinematics is only this particular matrix. Once we know this matrix, everything is done, because it's only substitution of the DH parameters into this matrix, then you get the transformation matrix. Any questions? So now you know about coordinate assignment, you know how to get DH parameters, and we know how to, if you know DH parameters, how do you get the transformation between two adjacent coordinate frames. So that is the basic requirement for forward kinematics. And the forward kinematics is basically, okay, so if you want to do the inverse also you can get. So if you want to k minus 1 to k, if you are interested in getting k minus 1 to k, it's basically an inverse of this one. And the inverse of homogeneous transformation matrix can be obtained by taking this R transpose and minus R transpose P. That is what we saw in the previous class. So the same application can apply here, and you will be getting it as a inverse transformation also. K minus 1 to k also you can get. That is known as the inverse transformation. Again, you don't need to, if you know this, then you can actually get it directly by taking the transpose, R transpose and minus R transpose P, you will be getting this vector here. Alright. So now let us see how do we get the direct kinematics or the forward kinematics of the manipulator. So as I mentioned, the point of interest is this point, that is the tooltip. We are interested in knowing what is happening to this coordinate frame, because we assume that the coordinate frame attached to the tooltip is this one, and whatever happens to the tooltip, the coordinate frame will be rotating or translating. So we will be able to get this point and the orientation of that particular frame by getting a relationship. So we are interested in knowing this vector P. So that is how far this tooltip is from the base frame. That is the position of this tooltip. So the position vector is of interest to us, and the orientation of this frame with respect to the base frame. So once we have this, we have the complete definition of the tooltip with respect to the base frame. We want to know the position vector and the orientation of the tool frame. Then we have the complete information of the tool with respect to the base frame. So we are interested in knowing this information. What is Px, Py, Pz, that is this tooltip with respect to base frame. So that is the interest. And then what is the orientation of this frame with respect to this frame. So assume that this is Zn, okay, this is Zn. So we are interested in knowing how this Z0, Zn and X0, Xn and Y0, Yn are aligned. So if they are aligned, you will be getting on 1, 0, 0, 0, 1, 0, 0, 0, 1 if they are aligned. Otherwise, you will be getting this as a normal sliding and approach vectors corresponding to the orientation of the tooltip. So this is finally what we are interested in. We want to know what is the position of the tool and its orientation with respect to the base frame, whatever may be the joint position. As a function of these joint variables, we want to get this Px, Py and Pz. So this is what we are looking for. So how do we get this? Is by looking at the joint variables q1 to qn. So I define the joint variables as q in this case because it can be theta or d. Any one of these can be a variable. So I generate it as a q1. So we have n variables because an n degree of freedom robot has got n variables. So given the variables values of joint variables, so the end effector location, that is the position and orientation in the Cartesian space of the robot base frame. Okay. So effectively we are telling that we want to get the transformation n to 0. What is this transformation is of our interest. Because this is the nth frame, this is your Ln and this is your L0. So we are interested to know what is the transformation of nth frame to 0th frame. So this is the transformation we are interested. And once we know this transformation, we can easily find out what is the position because this one gives you the position and this gives you the orientation. Now, the only catch is that in between you have many points and there are many variables. So, we need to find out how n to 0, how can we calculate n to 0 by using the individual transformation. So, now we have 1, 2, 3, etc. to n. We want to get Tn0 and we can easily find out what is T10, what is T21, what is T32 can be obtained from individual transformation. So, if we know the individual transformation, we can use this individual transformation to get Tn0 by simply multiplying the transformation matrices and finding out what is the relationship. So, we know T10, so I will write it as T10 multiplied by T21 multiplied by T32 n minus 1 gives me Tn0. That is the only thing what we need to know. So, if it is the n degree of freedom joint and if we can assign coordinate frame, find out all the DH parameters, we can find out the individual transformation between adjacent coordinate frames, and using this individual transformation, you can find out the final transformation Tn to 0 using this relationship 1, 2, 3, etc. This is the, and once you have this n0, you will be having the forward relationship. That actually this matrix will tell you what is the relationship of this coordinate frame to this frame, and we know that each one of these is a function of the joint variable q. So, this will be a function of not only joint variable, all the 4 parameters, this will be 4 parameters, this will be having another 4 parameters like this. So, this function finally this will be an expression, Tn0 will be an expression which has got all these parameters in that expression, and out of this only one of these will be variable. So, you will be having 6 variables and you will be having all others are constant. Finally, you will be getting Px as a function of all these parameters, you will get Py as a function of all these, Pz as a function of all these. This is the way how you will be getting the forward relationship, the position and orientation of the tooltip as a function of the joint parameters and the link parameters or the DH parameters of the matrix. Okay, so T and Q will be 10, 20, etc. So, now we are interested in the tool to base. So, this is tool and this is base. So, 1 to base, 2 to 1, 3 to 2, etc. n minus 1 will be the forward relationship for the manipulator. That is, if you know all the DH parameters, you will be able to find the relation between the tool and the base as the 4x4 matrix representation. Any questions? Okay. So, since I mentioned that we can have the first 3 degrees of freedom for positioning and the next 3 degrees of freedom for orientation, we can actually represent this also in this way between wrist and base and the tool and wrist. So, only for convenience, because the positioning is done by the first 3 joints and the orientation is done by the next 3 joints. We can represent this as 2 transformations, tool wrist to base and the tool to wrist. It's only for convenience, otherwise it is the same, only up to 3 we are bifurcating and then making it as 2. So, tool to the wrist, suppose this is the wrist point, then this will be 3 and then the first other 3 will be deciding the wrist position. So, the wrist position is decided by the first 3 joints and the orientation of the tool is decided by the next 3 joints. Okay, so finally the equation will be like this. A tool to base will be getting it as a 4x4 matrix with this as the position vector and this as the orientation matrix. So, your P will be this and your orientation matrix will be by this. So, that will actually having this 3 vectors. These 3 vectors will be the normal sliding and approach vector. So, this will be the normal sliding and approach vector. You will be seeing this as a 3 vectors, and that will be first will be the normal vector, sliding vector, and approach vector, and you will be having these 3 positions px, py, pz. So that gives you the p, and then give you the orientation of the tool frame with respect to the base frame. So this is what we will be getting at the end of this transformation. We are doing individual transformation between coordinate frames, and finally finding out the transformation from base to the tool. We'll take 1 or 2 examples to make sure that you understand this. So let us take an example of alpha 2 arm, which we already discussed in the class, how to get the DH parameter. So we don't go into that stage now. We'll see how to get the transformation matrix and how do we represent the position of the tool. So we are interested in this tool position and orientation. So we'll be assigning a coordinate frame here, as you can see here, there, and then you will be having coordinate frame here and a coordinate frame here. So these are the 2 coordinate frame will be assigned. We want to find out what is the relation between this coordinate frame and this coordinate frame as a function of all these joint parameters. So now we have different joint and link parameters. We have multiple parameters. We need to represent the relationship between these 2 coordinate frame as a function of all these parameters. So that is the forward relationship. So the first step in forward relationship is assign the coordinate frame. We saw how to do this. So you assign first coordinate frame here, next one here, then next one here, here, and the next origin will be the same place, the next coordinate frame, and finally your 5th coordinate frame will be at the tool tip. We are interested in finding out what is T50. So this is what we are interested in, and that should be as a function of all these parameters. So this is what we need to develop as a forward relationship. So we assign the coordinate frame and then get the DH parameters based on what we discussed in the previous class. So this is the parameters that we will get, the table of DH parameters that we have. So theta, since all are joint variables, all are rotary joints, we make this as a variable and write the equation or the relationship phi 0 as a function of theta. And since these are all constant, we will put all this into the equation, the direct relationship. So T phi 0 can be obtained by first finding out what is T1 to 0. So we find out what is T1 to 0, and then we write what is T2 to 0, then T2 to 1, then 3 to 2, etc. So since we have these parameters, we can easily write down the relationship T1 to 2 to 1, 3 to 2, etc. And then you multiply this and get the final relationship. So once you have these DH parameters, the first thing is to go for the 1 to 0. Okay, so 1 to 0 can be obtained by substituting these values of theta 1, alpha 1, A1 and D1. By substituting, this is your arm matrix or the transformation matrix, 4x4 transformation matrix between 2 adjacent frames. So this is what I showed you in the previous slides. Now substitute these values and then get what is the T1 to 0. Let's come. So what will be T1 to 0? Assume theta 1 is not known, so theta is a variable. So cos theta 1 can be written as C1. Okay. Then sin theta 1 is S1. Then this is A1. So A1 is given here 0, and theta 1 is not known. So this also will be a 0. A1 is 0. So this will be 0. D1 is there. So you can write it as 215, or you can write it as D1 also. Finally, you can substitute. So it will be 215. And then what will be this one? Alpha 1 is minus 90. So cos minus 90 is, what is cos 90? 0, right? So this will be 0. this will be 0, and sine minus 90, that is sine 90. Sine 90 is 1. Sine minus 90 minus 1. Yeah. So you will be getting it as the matrix here minus S1. So you will be getting it as, okay, return it as D1 itself. You can substitute the D1 and numerical value can be given, or you can write it as D1 itself. So this will be the T10 matrix. Same way you can get T21, you can get to T32 also. So T21 and T32 also can be obtained by simply substituting these values. You don't need to do anything other than that. Just substitute these values and then get the matrix 2 to 1 and 3 to 2. Okay, so finally the wrist to base. So if I bifurcate this into wrist and base, wrist and tool. So wrist to base is T. So if I write this as wrist to base, it will be 1 to 0, 2 to 1 and T3 2. That is going to be the wrist to base transformation. So multiply these three matrices, that is going to be the wrist to base relationship. That is the position of the wrist with respect to the base, and the position of the orientation of the wrist frame with respect to the base can be obtained by this transformation matrix, that is wrist to base. So you need to multiply this. This is maybe somewhere you make mistakes, but nowadays with all these symbolic computation, you can do it in a computer and then easily get it. So you can see here, this is A2C2 and A2S2, is A3SC3 and A3S3 for the positions. And if you go back to the picture and then try to understand, you will be able to understand why it is coming as A2C2 and A2S2, because you are trying to go up and down in the same plane. So your X will be A2C2 and Y will be A2S2. Alright, so we will get this as this relationship. So once you multiply this, you will be getting the wrist to base as a 4 by 4 matrix, and you will see this one, an expression just got cos theta 2 and theta 2 and theta 3. So C23 stands for cos theta 2 plus theta 3. So this is what actually S23, C23. This cos theta 2 plus theta 3 is given as cos 23. Similarly, sin theta 2 plus sin theta 3 is given as S23. So this wrist to base, so if I go back to that diagram, so it was something like this. One joint here, one joint here, one. This was the wrist point. If this is the wrist and this is the base, then you have this 2 degree of freedom here. The roll and the pitch. So the wrist point here, you can see this is the P, position of the wrist, and the orientation of the wrist is basically the frame attached to that. So this says that the position of the wrist is A2C2 plus A3C23 minus multiplied by C1, that is the PXW, and this is PYW, and this is PZW. That is the position of wrist in XYZ with respect to the base frame is given by this, and the orientation of the wrist with respect to the base frame is given by this matrix. So this is the position vector of the wrist point. This is the orientation of the wrist frame with respect to base. Same way you can get from tool to wrist also by multiplying 4 to 3 and 5 to 4. There are only 2 degrees of freedom for the wrist. So it will be, this can be obtained as T 5 to 3. Sorry. Or I put it as wrist. So 4 to 3, 4 to and 5 to 4. Okay, so that will be the tool to wrist. So 5 is a tool. You will be getting these 2 matrices multiplied. You will be getting, and you can see it's a function of D5 and S4. Similarly, C5 and S5. So it's a function of theta 5 and D, theta 4 and theta 5. Function of theta 4 and theta 5, and D5 is constant. So variable will be theta 4 and theta 5, and D is a constant. So you will see C4 C5 minus C4 S5, S4 C5 minus S4 S5. This will be the position of the tool tip with respect to base frame, with respect to wrist frame, and this is the X position of the tool tip with respect to wrist frame. This is with phi position with respect to wrist frame, and Z position. Because the rotation with respect to the axis of that position. So now we got these 2 transformations, that is wrist to base and then tool to wrist. Finally, we are interested in knowing what is the transformation from tool to base. So this is what we are interested in. Now multiply these 2 matrices. Multiply these two matrices. You will be getting the tool to base transformation, which gives you the complete forward relationship of the manipulator. And when you do this, again it will be the expressions will be slightly longer in this case. So you will be getting this as tool to base as this matrix relationship. So this is the final transformation matrix between the tool frame and the base frame. You will see that the Px is given by this, the position of the tool with respect to base Px is given by this is Py and this is Pz. So Px is equal to cos theta 1 multiplied by 177.8 C2 plus 177.8 C23 minus 129.5 S234 will be the Px. Now we can see that the position of the tool tip Px is a function of theta 1. So as the first joint changes, its Px changes. As theta 2 changes, it changes. Theta 3 changes, position changes. Theta 4 changes. And it's not a function of theta 5 because theta 5 is the roll axis. The roll axis is not going to change the position of the tool with respect to the base frame. That's why Px is not a function of theta 5, but it's a function of theta 1, theta 2, theta 3 and theta 4 plus other parameters, fixed parameters. Similarly, here you can see Py and this is also Pz. Then this is the orientation of the tool frame with respect to the base. And here you will see it changes with respect to all the joint angles. So theta 1 to theta 5, it's a function of theta 1 to theta 5. So any changes in any one of the joint angles will change the orientation of the tool with respect to the base frame. Pardon? Column? This one. Yeah, so this one, right? Yeah, so why is it so? So what is this vector? This is an approach vector. Right? So approach vector is, so I am holding this is approach vector. And any rotation of this, okay, so it's not going to change. Okay, so it's going to be the same one. So theta phi is not going to affect along that axis. The approach vector is not going to change. This vector will remain same even if I rotate like this, right? But if I rotate with respect to this, then the vector is changing. Okay, so that's why the approach vector is not a function of theta phi. Okay. So you can actually go back to the diagram. Yeah, now look at this manipulator. So this is the approach vector, and even if you rotate with respect to this vector remains the same. Vector is not going to change. And similarly, you can see the position of this is a function of theta 1, theta 2, theta 3 and theta 4. Theta phi is not going to affect the position, okay, because theta phi is again rolled. So the position will not get changed simply by rolling this, having that roll motion. So that is why it is the position is independent of theta phi, and orientation of course gets affected. Now you see all these parameters are actually there in the relationship 129.5, 177. Alpha has been taken already into account. So finally you have the relationship. Now what is the benefit of having this relationship? Now you don't need to worry about the orientation of the robot or anything. Now you have a complete mathematical representation of the position and orientation of the tooltip. For any value of theta, you can actually find out what is the position and orientation of the tool. Whatever may be the values, if they are within the limits of the rotation, you will be able to find out the position. Now, if we have a manipulator, if we have a robot, and we want to find out its what are the points it can reach, you simply substitute the values of theta 1, theta 2, theta 3, theta 4 in whole range. You will be able to see all the points where actually it can reach. That actually becomes the workspace of the manipulator. So for any value of theta, you will be able to get this relationship. I mean, the position and orientation of the tool can be obtained for any value of theta. So this is not a forward kinematic relationship for this particular manipulator. So for any given manipulator, you will be able to find a relationship like this. Once you have designed the manipulator, then this will be fixed. Only the theta or the d can change, all others will remain same. So you will be able to represent the position and orientation of the tooltip as a function of the joint variables, either theta or d, and get the position and orientation for any value of these joint variables, and that is known as the forward kinematic relationship. Because you know theta or d, you find out the position and orientation is the forward relationship. Okay, any questions? Fine. Okay, so if you understood this, please try to solve this. I will help you. So please look at this 6-axis robot. You have to find the position and orientation of the tool at the soft home position shown below for the 6-axis articulated arm IntelliDex 660T. So this is a commercial robot arm known as IntelliDex 660T. It has got 6 axes. Only difference is that you have a roll here, a shoulder roll here compared to the other robots, and then you have a tool roll also here. And you will see that there is a tool pitch here, but there is no tool yaw in this case. You don't see a separate tool yaw axis here, but instead you will have a shoulder roll in this case. So it has got 6 axes. So do you think it has all the 6 degrees of freedom, or is it a redundant manipulator or a manipulator with less number of joints than required? Because you don't see a yaw joint here, right? Yaw axis. So you'll be able to position the tool with any arbitrary yaw. Yes or no? You understood my question or not first? Okay. So whether you consider this as a holonomic one or a non-holonomic one? So one advantage here is that you can actually use this shoulder roll. The shoulder roll can be used to convert this axis to a yaw axis. So if this is the current elbow, or this is the elbow, you have a pitching. Now this is the pitch axis, but if I want a yaw, I just rotate it like this and then do this. Now I got a yaw axis. So this can actually act as a pitch or yaw axis by using the shoulder roll. So basically, you are having two roll axis and in between a pitch axis. So you will still be able to control the yaw because we have an additional roll here which can position it using can control the yaw using this joint. So effectively, it has got all the 6 degrees of freedom. So it can actually be, it's actually ergonomic one. Yeah. Yeah. So that is the question I am going to ask you. Okay. So let us see how to assign the coordinate frame here. The first thing to do is to assign coordinate frame. Okay. So we know that how to do this. So we'll start with this. Okay. So this will be the Z0, X0, and I'll call this as L0. Now you have a shoulder roll and a shoulder, we call it a shoulder pitch. Okay, this is shoulder roll, this is shoulder pitch, and then elbow pitch, and then tool pitch, and tool roll. So that is the way how it is defined. So we need to look at each okay, you can assign this as the first one or this as the first one depending on how you assign it. Either you take this as the second axis or this as the second axis. The next one as the third axis. Now you have to see the same principle you should follow. So your axis will be like this, your Z will be like this, and this will be the Z. So you will be getting a frame here, right? And origin will be there. And once you have the Z axis, then you assign the X axis and Y axis based on the principles. It should be orthogonal to this. Go with the same procedure of or follow the same rules, you will be getting the coordinate frames. So I am assigning this as the Z1 axis and you have the X1 and Y1 because X1 should be orthogonal to Z0 and Z1, and therefore you take X1 in this direction and then you assign Y1. And the next joint, where will be the next joint? The origin, you have to see first the origin. So the axis will be this one, right? That will be the Z axis and this is the Z axis. So they intersect at the same point and therefore we will be having it at the same origin. It will be at the same origin and then go with the same rule. Okay, so you will be getting it as Z2. Okay, I have taken this in this direction. As I told you, we can take in this direction or this direction. So any direction you can take. So this is Z2, X2. And follow the procedure, you get Z3, Z4 and then finally your Z5 and Z6. Z5 and of course you have to assign it here also. Yeah. So this is the way how you assign coordinate frame. So I have not done anything new here. Whatever we discussed in the previous classes, I just did it without going into the details. How did you get each one of these? So as you know, Z2, this axis and this axis, they are parallel. The joints are parallel. Therefore, you get Z2, Z3 and Z4 in the same direction. And then, since the origin is at the same point, Z5 is in this direction, the tool roll is in this direction, and therefore, Z5 and the ZX, Z4 intersect here at the same point. So we take the same origin here and then assign the other axis. And finally, the tool tip will be here, Z6. So that is the way how you get the, oh, okay, time to stop. So this is the thing. So now get DH parameters. So I am giving this to you. So please find out the DH parameters and bring the DH parameters tomorrow. Then we will see how to develop the forward kinematic relationship for this. So once you get the DH parameters, then there is nothing to do other than the matrix multiplication. So get the forward kinematic relationship for this approach. Okay. All right. So we'll see you tomorrow morning. Thank you.